6. All right. So the first lesson that we talked about after, I've been seeing some red, so I'm going to use maybe purple. Oh, okay. So with rational functions and end behavior, it's easier. Now that yesterday we re-highlighted that rational end behavior is just based off of polynomials. Okay, so you will see, if you had written this down, that the limit as x approaches positive negative infinity, you're dealing with the leading terms. This is the most important thing in this lesson. That the leading term of the numerator divided by the leading term of the denominator will give you the end behavior of the rational function. Now, it's important to recognize that this end behavior, if we're connecting it to two other things, we are connecting it to horizontal asymptotes and slant asymptotes. We talked about slant asymptotes in topic 11. Okay. So we did see this again. And noticing that the difference of the degrees will tell you what type of end behavior you're going to have. So if the numerator degree was 2 more than the denominator, you got a quadratic. If the numerator degree was 1 more than the denominator degree, you got a linear, right? See right there, slant asymptote. In this lesson, we didn't find what the slant asymptote was, but we saw it was connected later on. Okay. And then we went ahead and we practiced finding the end behavior using that limit notation. Okay. Now, just as we talked about end behavior with limitation yesterday, remember, as input values increase without bound, as x values decrease without bound, that's the verbal language behind x approaching positive infinity and x approaching negative infinity. Okay. End behavior, this would be, if this showed up anywhere on Fourier response, which one, I'll tell you, which one do you think end behavior would show up? I see a 3, which is periodic context. See some 2s. It is 1. FRQ1, because end behavior is a function concept. Okay, you theoretically could see end behavior being applied in a modeling context with FRQ2, but if I had to put my marbles in one of the 4 containers, it'd be number 1. Okay. Rational functions and zeros. You have to know how to factor. Okay. Factoring quadratics needs to be something you're able to do. Something like part C down there, x cubed plus 2x squared minus 24x. You should notice you're pulling out an x and then you're factoring a quadratic. Okay. That is the only 3rd degree. Theoretically, you could do a 4th degree if it was like x to the 4th, x to the 3rd, and then x squared. You factor out a x squared. But for the most part, from what I've always seen on AP Classroom and with other things out there, if they give you a cubic polynomial and it doesn't look like this, they will factor it for you, which is really nice. Because otherwise you're like doing P over Qs and things like that. So like we didn't talk about this class at all. Inequalities, sign chart, obviously we've seen that is a very important tool. And remember, inequalities, multiple choice question. Okay, multiple choice question. And using those sign charts, using zeros, using vertical asymptotes. Um, so, and remember that what we used in polynomials, using the exponents to figure out if it switch between the intervals, that still works here as well. So looking at multiplicities, okay. So that was 1.8. 9 and 10, vertical asymptotes and zeros. So this is obviously what we just talked about with the kind of the justification. If the denominator, if all those factors disappear, it's a whole. Okay. Oops. There's a denominator disappear, wholes. Okay. If there's anything left over, it's a vertical asymptote. Okay. This is also where we talk about left and right hand limits. Okay. Left and right hand limits. I've even, to prepare algebra 2 for this next year, I started introducing them to, that's don't know the notation yet, but I've started introducing x approaching 1 from the left, x approaching 1 from the right. So then when they get to this, it's easier. And so for asymptotes, wholes, multiplicities, a bunch of good stuff there. So vertical asymptotes and wholes could show up in FRQ1 because you're dealing with like undefined values. Okay, undefined values. So that's where it could show up, isn't it? In a free response style question. Um, um, like for here, x plus 2 over x minus 3 squared, like if that was a function that they gave you, and say you had a composite function and you plugged into G3, you would have no value, okay? You wouldn't be able to compute that. So 11. 11 was a summary of everything we had already talked about with polynomials and rationals. Now, there was one part of this lesson that we have not covered yet. I'm not going to cover that today. I'll probably cover that at some other time. I may also just give you an AP classroom video or a video somewhere else. Last year in Algebra 2, did we talk about Pascal's triangle? A little bit. Just a bit. Like like 1 1 1 2 1 1 3 3 1 1 4 4 1 4 6 4 1 1 5 10 10 5 1. Did we talk about that last year? Yeah, but I don't remember. Okay. It's Christmas tree. No better time like the present. Okay. So the second portion of this lesson is called the binomial theorem. Okay. This is 3 pages. So if you want to write this like on the back of the last page, you can do that. So the binomial theorem is a theorem. The binomial theorem, binomial, 2 terms. Okay. The binomial theorem is a short-handed way to expand any polynomial. Okay. So whether that's like x plus y squared, x plus y to the third, x plus y to the fourth. Now, we've all seen quadratics before, where it is like x plus 3 squared, right? The squared, the exponent, refers to the second row of Pascal's triangle. Okay, so like this would be n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Okay, notice how the first number in that column are ones, the second number 2, 1, 2, 3, 4, 5. No coincidence that they match up. When we learned about shortcuts in algebra and saw them in algebra 2, I knew that this same one is x squared plus 6x plus 9, right? When I do that shortcut. One way that we talked about that shortcut was like this. Was like that, right? We squared the first term, we squared the last term, and then I took a product of the middle and then doubled it. Does so when we take a look at this kind of unsimplified form with all the terms, check this out. 1, 2, 1. The numbers, here, I'll put that in parentheses. There. So what is worth recognizing here is that the 1, 2, 1, that is a pattern for every quadratic. Okay. Now, what if this was x plus 3 to the third? Oh, I don't want to FOIL and then have to distribute. Let's go to this third line right here. Okay. If we are using this third line, my pattern is going to be 1, 3, 3, 1. So there are going to be 4 terms in my answer. 1, 3, 3, 1. Now, I made this a little bit easier because to make it plus. Okay. Now, here is what is the unique relationship between the terms and the exponents. If I zoom in here to the 3 and the x and think about them individually, what's the multiplicity on 3? It's 1. What's the multiplicity on x? It's also 1. What's 1 plus 1? 2. 2. 1 plus 1 is 2. Ooh, 2. This one, 1x, the multiplicity here is 2, because this is then 3 to the 0. This one out here is 3 squared times x to the 0. So the sums of the exponents are always the same as what you begin with. So let me demonstrate this. If I do 1, 3, 3, 1, this first one, before I do all the simplifying, it's 1 times x to the third times 3 to the 0. 3 plus 0 is 3. This is a plus. What do you think the next combination will be? And notice how this went from x squared to x to the first. So if this is x to the third, what would the exponent be here? This one went from x squared to x to the first. So if this is x to the third, x squared. So then what's gonna be the exponent if it's 3 to the 0? What's it gonna be here? 3 to the first. What's 2 plus 1? 3. What's gonna be the exponent on x in the next term? Yes, you said 1. You said 1, right? Oh, I thought you said 1. 1. 3, 2, 1. What's the exponent on 3 gonna be? Squared. Sorry. Plus 1 times, yes, x to the 0. Good job, Jackson. And then this, oh man, we're running out of room over here. And then 3 to the third. Oh, whoa. There we go. Oh, shoot. Oh, we're right there. Oh. Gosh, 3 to the third. Yeah. To the third. All right. So let's simplify the terms. X to the third. X to the third. What's 3 to the 0? It is 1. Plus x squared, right? Oh, now it's 3 times 3 to the first. What's 3 times 3? 9. So that's 9x squared. What is that next term going to be? It is 27.
Oh, yeah.
No, and then what is the last term going to be? Good. X to the third, x squared, x to the 0. This is the binomial theorem. So this is x plus 3 to the third. There are AP classroom questions that you're going to see on the progress check where you are going to be doing some expanding. One other thing about this is they can ask you about particular pieces, okay? Like dealing with like the coefficient and things like that. So this is what the reason we didn't cover this at this time was because it had been quite a while since we had done polynomials. We were in the thick of rational functions, so I didn't want to distract you with this. So, right. But then yeah, after this we just did long division, finding asymptotes, finding holes, stuff we had already done before. Example 2, example 3, you are kind of dealing with kind of some AP style questioning that you give a function and I ask you about a different function, okay? And then I think my favorite problem out of all of this is slant asymptote, okay? What is the rate of change, the slope of the slant asymptote? Because that is a problem that looks hard, but is so easy, okay? So that was equivalent representations. Transformations. This is now the 4th year. I am going to say 4th year, even say 5th year, where you've talked about transformations. You see some transformations in pre-algebra to some degree. You definitely see them with me in algebra. You see them when you change shapes in geometry, making them bigger, making them smaller, reflecting them, moving them around. And then you saw them in algebra 2. So lo and behold, you're number 5. If you want to say 4, that's okay. So transformations, if you're going to see this on the AP exam, more than likely it's going to be a multiple choice question. In the first response, they're not asking you to construct a function based on transformations. So keep that in mind. But there are three transformations: translations, dilations, and reflections. Okay, so manipulating a function in different ways is going to be important. Um, uh, Building a function, and maybe they are asking you to, maybe they're asking you to, you're like, give them a function, they give you some transformations, and then you choose from multiple choice. Which of these functions models the transformations? We did also have some problems where we are solving some equations, finding some zeros. I think seeing something like some of these things, I think would be a little bit of a stretch on the AP exam, but this is just trying to get us to think like, how can we work with how can we work with transformations? So that was number 12. 13 and 14, modeling. Okay. Now, so we grouped these together because there is a lot of overlap. A few things worth pointing out: you'll never have to graph and create a scatter plot on the AP exam. Um, but you will sometimes have to make a model to answer a question. Okay. Some of this was a little bit of review because we talked about linear and quadratic models and how we can see those in the table. What I will point out is this: applying a function model to answer questions about a data set or contextual scenario. And remember, data set, contextual scenario, we're talking about a story problem. Okay. It is this piece right here where you are dealing with average rates of change and estimates. Okay. That's where they will sneak in some of those problems. Here's the other thing to remind you / tell you again. This applying a function model, if you remember the warm-up from last week, when they like identified that that was an exponential model. No, that was a logarithmic model in the context of the entire FRQ. They were using 114C as an indicator for a logarithmic model. I understand that we don't see logarithms until unit 2, but this applying a function model, you can talk about whether it's a function from unit 1 or unit 2. Okay. Oh, thank you. So we talked about how did we see some tables with patterns, how did we construct a piecewise function as well. We're remembering that point slope form is the best form. Oh, yes, perfect. Example 4, we already have it labeled, maybe from when you were doing test review, talking about creating a quadratic. Use the given data to write 3 equations that can be used to find the values for A, B, and C. You have to use a calculator to find A, B, and C in a context like this. The reason that is the case is because I don't have an expression that gives me C equals a value. That would only happen if an input I was given where the input was 0, which would cancel all the variables for that particular equation. But then even here, well, that's a typo. Calculate the average rate of change. This is that 14C applying the model in different scenarios. And it's also worth pointing out that in this model for this problem, You don't need to know what the actual model is to find the rate of change. Now, the only other thing that we could have used here is using the rate of change to predict the value, to predict a value between $13 and $16. We would not use this rate of change for 13 to like 17. So constructing a rational function, I've seen just only a little bit of this. And then lastly, just applying some of those things. And again, rate of change, you are given a function, okay, in that scenario. So yeah, so applying a function model, rates of change is huge. So okay, that's what I've got for you today. Okay, so I will say at this point, you should be like, if you didn't start yesterday, today, start working through some of those progress check questions. Um, um, and just it's important to remember that like as we go from one day to the next, don't feel the pressure to like between today and tomorrow have the progress check for these lessons done by tomorrow. Okay, don't feel that pressure, but just be working on them continuously, giving I'll say giving half an hour, 45 minutes, an hour going over things is going to benefit you in the long run. Tomorrow, when we come back in, I will give you practice sets of multiple choice questions from Unit 1. We'll practice through them. We'll talk about them. You can expect 5 or 6 of them. So you kind of working them on your own, then we're working on them together. So, all right. Hope you all have a good rest of your day.